starting. So welcome everybody, thanks for coming. Our speaker today is Alessandra Pluda from the University of Pisa, and she will talk about resolution of singularities of the network flow. Thanks a lot for being here, and please go ahead.
Thank you very much. It's a great pleasure to give this talk in this online seminar. So today I'm going to talk about the project with Giorgio Lira, Rafe Mazzeo, and Mariel Saez. But it is about the resolution of singularity of the network flows. But to talk about the singularity, we have before to talk about the network flow. So I started studying the network flow several years ago during my PhD. And I have studied several different aspects of the flow. And starting from the well-posedness, so if we have this problem, this PDE problem, what can we say? There is existence and uniqueness, and we have some positive answer. In the case we work in sublet spaces, and this is work done with Julia Menzel from Regensburg and Michi Goswein from Duisburg-Essen. And then we have to arrive to the core of the topic, which is the singularity. So after we have the well-posedness result, that is, the flow started, it's smooth, it's nice. Then there is at some point a maximal time of existence, and at this maximal time of existence, singularity happens. We have to describe what are singularities. We have to find example of singularities. And I've worked about this topic with Carlo Mantegazza and Matteo Navaga, that were my PhD advisors, and Felix Schulze. And then after we have a quite good understanding of a singularity event, we want to go past singularities. So we want to define a flow remaining still in the framework of classical PDEs that goes past singularities, similar to what has been done for the curvature flow with surgeries. And this is the content of the project. And so this is the content of the paper, but we have written with George, Rafe, and Mariel. And clearly, if we are so lucky that we can go through these singularities and we can restart the flow many times we want, then we have the opportunity to speak about long-term behavior and what happens as the time goes to plus infinity. And to describe what happens when times go to plus infinity, there are several tools, and we are in particular developing a tool, the Loyazier-Simon inequality, for this flow with Mark Pozzetta, but this is still a work in progress. So today I want to talk about the paper with George, Rafe, and Mariel, but to talk about this, it is necessary to introduce to you the flow. And so I will talk very fast, but also about the other things here with these co-authors. So first of all, to fix the idea, what is the network flow? One of the recent success in the study of flow has been the result by Gage and Hamilton and Grayson about the curve shortening flows. What is the curve shortening flow? Consider a curve in the plane, can be also in Riemann manifold or in Rn, but for simplicity, today we will work only in R2 with Euclidean metric. And we want to let evolve this curve in the direction of its curvature. So this is the one-dimensional analog of the curvature flow. And since we have only one curve, we have only one curvature. We don't have the mean curvature vector, but we have the curvature. And the prescribed velocity at any point in time is exactly the curvature. I want to underline the fact that it's the normal velocity that it is prescribed. So there are some tangential degrees of freedom in the description of a problem, because this problem is geometric and there is an invariance under the parameterization. What does this mean? This means that if we have a solution, and when we reparameterize this solution, we have another solution. So we can simply construct solution by reparameterizing the curves. So only the normal velocity is prescribed. This evolution can be understood as the gradient flow of the length. So what does this mean? That we are looking at the movement that goes in the steepest descents with respect to the L2 gradient of the length. So the evolution is minus the gradient of the length. And so since we have this variational point of view in mind, it's clear that the length decreases in time. So it's easy to compute the evolution equation for the length, and we clearly obtain something that decreases in time with a sign and minus sign. So this is a point of view that is crucial to then go describe what is the network flow, because it will be extremely important to define the network flow to allow us to have a good definition of the flow. So what is the theorem? The theorem by Gage, Hamilton, and Grayson is as follows. So if we have a simple causal curve in the plane and we let it evolve by shortening flow, then at some point it becomes convex. And then when we have a convex curve, we know that the curve becomes rounder and rounder. And the circle becomes smaller and smaller. So at some point, any causal curve in the plane is going to evolve and to disappear to a point. And if we do a blow up to this point, we see the shape of the singularity. And we realize that with a proper suitable definition of blow up, we will see a circle. So here it's a picture that depicts the evolution of a curve in the plane, and this axis is the time. So we see the evolution in space and time. So this was a extremely interesting couple of papers, and was one of the really early success in the field of flows, and was clearly motivated by differential geometry arguments. So it's a flow that is extremely interesting in itself, but my flow, the flow that I'm going to talk about today, the network flow, was also motivated from more applied aspects of mathematics. So the idea is that this flow has been introduced by Mullins, that was a physicist in metallurgy, that want to describe the evolution of grain boundaries. So the grain boundaries of the crystallite metal, we know that when they are heated, they are hot, then they move. And they move with velocity that is proportional of the curvature. What does this mean? What is this picture? This picture wants to represent a polycrystal. This means that it is a material that at the structure level has different orientation. So we can see this like the orientation of a material. And what is this boundary? This boundary is the grain boundary, and it is exactly where two grains with different orientation are touched. And if we yield this metal, what we are going to see is that these different orientation are going to become more similar and similar during the evolution. So they want to become more aligned. And to describe this phenomena, one can look at the boundaries and describe the evolution of the boundaries. So this is has been proposed in the 50s, and a definition of weak motion by curvature has been proposed and studied by Bracke in this seminal paper. And in that case, he was able to obtain a global in time solution. However, this solution was extremely weak. Even something like the empty set could be a solution, because he has a definition of the flow, but it is done with inequalities, and it is extremely weak. So it's not really, they are not really surfaces that evolve, but something weaker. So this motivated all the study later, because one would like to let evolve real surfaces, not very fault or something so weak, but having really surfaces that evolve in time. And in order to do so, we need a better definition or a stronger definition. There are different ways one can try to approach the problem. And it also depends on the fact if you want to look at the grains or at the boundary of the grains. So there are some type of definition that are still weak definition, but not as weak as the Bracke flow, that are the so-called BV solution, that are focused on the evolution of the grain. So they look at the sets that evolve, not at the boundary that divide the sets. And these are solutions that has been defined by Esdoglu and Otto, that in a paper of some years ago, show that this kind of definition can be can stay in the realm of minimizing movement. And there are several recent very interesting results that try to say that this solution is not so weak as one can think. And how they have done, Fisher and Sellout and Simon, they have done a unique, weak-strong uniqueness result. So they say, yes, okay, it's true that our solutions are weak, but they coincide with a strong evolution. Okay, to say they coincide with a strong evolution, we need to have the classical solution definition, and it's what is my point of view. This classical solution definition focuses on the evolution of the boundary. So if we are in 2D, you can see here that the boundary of a grain, it's a network. It's a union of curves. And this type of definition of solution has been introduced by Brons and Deraitis. They have had in mind something slightly different because they were focused on the singular limit of the Allen-Kahn, of a multi-phase Allen-Kahn evolution equation. However, we found their definition extremely useful, and so we study a lot this problem. Other people that work on this are also Illman and Neves and Schulze, but they have a nice result, also a way to define the flow past singularities. When I studied this problem during my PhD thesis, and in higher dimension, there is a paper by Debner, Garkin, Kozaka, the study the well-posedness of the flow in higher dimension. Then the last point of view that has been proven extremely strong, extremely good very recently, is the one that puts together looking at the boundaries and looking at the grains. So there is an evolution equation for the boundaries, but it is the Bracke flow. But since the Bracke flow was too weak and we have phenomena like sudden loss of mass, Tonegawa and Kim and then Tonegawa and Stewart, they have introduced also an evolution for the grain. So they look both at the evolution of the boundary and the grain. They say something also about the grains. And there are very recent interesting results. In particular, they are able to say that they have a global solution that is weak, but it's not the empty set, and there is not a loss of mass.
So
Okay.
I had a
Yes?
question. When you say controlled motion of the grains, do you mean they change the equation? Or do you mean that they impose some sort of auxiliary condition so things don't vanish, or what?
They have some auxiliary condition on the grains. They have the same equation, which is the Bracke flow, but then they have something related to the evolution of the grain. So they don't have an extra equation. So this is
Separation properties or something.
Yes, it's not
Okay,
possible
yeah.
to add an extra. We have also something similar because we have to study what happens at the evolution of the boundary, and you cannot prescribe an extra equation, but you can prescribe extra condition. I'm going to explain in which sense. Okay, so let's focus on my point of view. My point of view is to define the flow with classical PDEs. And clearly, if we want to describe the flow with classical PDE, we have to write an equation for each curves. But when you use this point of view, it's very difficult to treat topological changes. So if during the flow, the curve disappears, that is going to happen, then you have to it's not so easy to define the flow with some equation, because if you have an equation, one of these equations, the curve that is driven by one of these equations disappear, then that equation has not any more sense. So we have to come up with another definition. So the definition that we are doing is as follows. We suppose that there are some singular times, and we suppose that they don't accumulate. So this is not something that I'm able to prove. I have to suppose this. So I suppose that I have some singular times. Then I suppose that between two singular times, my curves evolves solving the curve shortening flow for each curve plus boundary condition. And then I have to require some continuity through the singularities. So if I look at the network that evolves as a set, I suppose that it is continuous also at the singular time. I cannot suppose too much because we are going to see that there are some jump of the angles when I pass through a singularity. So I cannot suppose that it is a smooth evolution because I have topological change and change on the unit tangent vector. So I want to state what is the dream theorem, what I would like to prove if I have a completely understanding of the problem. However, we are not so far yet. We have done several points of this dream theorem, but not everything. And probably as it is stated, it is also false because I try to state it in a very simple way. It cannot be so simple, but at least I can give you the idea of what I want to do. And then after that I state this theorem, I start from the very beginning and I start from defining the flow. Okay, what is the idea? What we want to prove? We want to prove that if I have an initial network that is regular enough, smooth enough to my purpose, then there exists a solution that it is a maximal solution, so there is a maximal time interval with time positive, and then there is a discrete set of times, and this solution is continuous in the entire time interval, and solve the curve shortening flow between two singular times. Then there is the possibility that my entire network disappears at some point. So if all the curves disappear, then the flow stops. In all the other cases, I hope to have an existence that is for every time, so global existence, Tmax is plus infinity. And what I want to prove, that there exists a limit for t that goes to Tmax, and this limit is a critical point of length. And I want to prove that this is a limit, not up to subsequences. And clearly, I cannot prove that there is uniqueness, because the uniqueness is false. We will see that I have a theorem that states a multiplicity of solutions, so I cannot have uniqueness. But I want to show that non-uniqueness is only present at singular times. So between two singular times, nothing bad happens. I have only one evolution, and then at singular time, we can have also multiple flow outs for how to exit with singular times. Something that we are really far from proving is that singularities are completely classified. We have a lot of examples, but we don't have complete classification. And then what is the content of a paper with Georges, Rafe, and Marielle? When we arrive at singularity, we are able to restart the flow, and this restarting is classified. So this means that maybe there is not a unique solution after singularity, but we are able to classify the solution. So this is what one wants to prove. And from now on, from the remaining time, I'm going to explain you what we are able to do till now. And so you will also know what are the open questions that are the questions that are remaining open. Okay, so first of all, I have to define what is the flow between two singular times. So first of all, what is a network? A network is a connected set in the plane, and it is composed by finite remaining regular embedded smooth curves. With regular, I mean that the curve is at least C1 and that it is in immersion. So gamma dot is different from 0 everywhere. And smooth, with smooth, I mean smooth as I need. Something slightly less than C2 will be enough, but more than C1. And what is the difficulty of this of evolution of this object is related to the fact that I have curves that are really easy to treat, but these curves meet at varying point in junctions. And so these junctions are kind of singular points. So this object is not a manifold, it's not something completely smooth, even if all the curves can be parameterized by smooth map. Since I want to write an equation, a PD equation, I have defined the network as a set. However, I have to think of parameterization. So I will work with the function that parameterize the curves. And since we are in one dimension, it's not difficult to say. It's clear that each curve admits a regular parameterization. And are from 0, 1 because what I'm doing now. But you can have also non-compact branches. So it's not the case that I've treated in this slide, but can be done. Okay, so how we arrive to define the evolution, we have to keep in mind that the flow is a gradient flow of length. So the fact that the flow is the gradient flow of length tells us, or at least formally the gradient flow of length, tells us that the normal velocity is the curvature, exactly in the curve shortening flow. And again, only the normal velocity is prescribed. And we have also some extra condition at the junction. First of all, if we want to write something that is energetically reasonable, we have only triple junction. And at the junction, we have that the sum of unit tangent vector sum up to 0. So these conditions are energetic conditions, are related to the fact that the problem is variational. So what we have an equation, a main equation for each curve, and then we have a boundary condition at the junction. Then, okay, if we have some endpoints of order 1, they can stay fixed in the plane. So we can have some Dirichlet boundary condition, or we can work inside of a convex set, and we ask that the endpoints meet with 90 degrees the boundary of a convex set, or we can work also in the entire R2, but we have to ask that at infinity the non-compact branches converge to some half lines. Okay, I told you that the condition only triple junction and 120 degrees at the angle are variational. In which sense? So if we consider the first variation of the length, we have this part here, but it is minus the curvature. And if we want to understand the flow as the gradient flow, so we want to move in the minus gradient direction, then we need to understand this object like the gradient of this one. And so we need that this part of the boundary condition is 0. So we have a sum at the boundary of a unit tangent vector sum up to 0. So this is variational condition. And so we have the sum of unit tangent vector that are sum up to 0. And why I consider only triple junction? Well, because if I have a quadruple point, I can easily realize that if I split the quadruple point into triple junction, then the length is going to decrease. So the energy of this object here with 2 triple junction is less than the energy of cross. For this reason, I asked to work in the class with triple junction, at least for the very beginning. So our result with irregular network clearly is not treating the case of triple junction, but we start in the class of what I call regular network. So only triple junction, only 120 degrees at the junction. Then I want to prove a well-posedness result. So I want to prove that at least for a short time, the flow exists and the solution is unique. Clearly, the solution can be unique only up to the parameterization, because as I told you before, the problem is geometric. If I take a solution and reparameterize, I get another solution. So my only hope is to prove that if 2 solutions are different, they only differ by a reparameterization. Moreover, I told you that the evolution is only normal. This means that the normal velocity is prescribed. In particular, the evolution cannot be only normal, because I have at the triple junction the sum of unit tangent vector that is 0. So I'm in the plane. So I have also that the sum of the unit normal vector is 0. And if I have the sum of a unit normal vector that is 0, I want that the junction remain a junction. Every curve move only in normal direction with the sum of the normal equal to 0. Then this means that the triple junction does not move at all. This is not the case that I want to describe, because I want to decrease the global length of the network. If I fix the junction, then I have a much simpler problem, not so interesting. I'm only minimizing the length between the endpoint and the triple junction. And if you also think from the PDE point of view, it's also overdetermined. So it's clearly not a good problem, because I have a junction fixed and sum of the unit tangent vector is 0, too many conditions. So this is not the point. So this makes clear that the evolution is not only normal, but we have also a tangential components of the velocity, but it's not prescribed. So it's not prescribed, so I can choose whatever I want till some the boundary conditions are preserved. And this is important because if I choose a suitable tangential velocity, then the problem becomes much nicer, because it becomes the T of gamma equal to second derivative of gamma divided first derivative of gamma squared. And this is not anymore degenerate. It's a nice non-degenerate quasi-linear parabolic equation. So I take this advantage to choose the tangential velocity, and I arrive to this flow that is the so-called spatial flow. And at this point, it's not so tricky to prove well-posedness. So in particular, there exists a uniqueness for short time. From short time to a maximal time interval, so it's not difficult to pass from short time interval to a maximal time interval. So what we have, that if we have an initial network that it is at least of class 2, then there exists a maximal solution of the flow. And it's also geometrically unique, what we wanted to prove, and also smooth for all positive time. And this is something that it is expected because the flow is parabolic. So we gain smoothness for all positive time. The proof of the fact that the flow is smooth for all positive time is a bit trickier than expected because we have this boundary condition that are fully nonlinear boundary condition. But the result can be proven as well. So how we prove this theorem? We go from network to parameterization. Namely, we choose the tangential velocity as we wanted. Then we prove the well-posedness of the spatial flow. And then we prove that two different solutions differ only by the parameterization. So to obtain the result of existence and uniqueness with C2 initial data, I have to take an initial data. So I have to combine several pieces to get existence and uniqueness. So one can start from the result by Bronzer-Deritis that find a solution if the initial datum is C2 plus alpha and there's extra boundary condition. So there are the condition like this, that if you read in a geometric way means that the curvature are equal at the junction. So since I want to be C2 plus alpha till the initial time, I need also extra condition at the boundary to be at least C2. So we prove with a linearization argument plus fixed point that there exists a solution. Then with an approximation argument of a spatial flow. Then with an approximation argument, one can obtain existence for C2, but in this approximation lose uniqueness. And then to obtain uniqueness, we have basically redone the short time existence result in sublet spaces. So we start with the datum that it is in W2 minus 2p p. And I ask that p is bigger than 3 because I want that I have that the space embedded into C1 because I want to write pointwise the boundary condition also at the initial time. Then with this initial space here, the reasonable solution space is this one, W1P LP intersected with LP W2P. Basically, we are saying that we have 1 week derivative in time and 2 week derivative in space. And in this solution space, I can prove existence and uniqueness for a short time of the flow. What it is interesting that the time of a short time of existence depends on some condition of the initial data. So in particular, depends on the semi-norm W2 minus 2p of initial datum. That is kind of reasonable because it's the only norm that we control, semi-norm that we control. And also depend on the minimum of, sorry, here derivative is missing, of sigma x, derivative of each curve. Why? Because if you think about the equation, I have 1 over gamma x squared. So I have the derivative at the denominator, basically. And then, okay, we can also prove that the flow is positive, is smooth for all positive time. Again, the structure of the proof of this result is exactly the same of Bronzer-Deritis. So linearization, show existence of a linear problem, and then with the Banach fixed point theorem, we construct a contraction, and we show that we have a fixed point, and from this fixed point we can find the solution. Okay, this is the more standard part. Now we go closer and closer, we arrive closer and closer to the interesting part of the talk. So first of all, I want to describe what happened as singularity. So the tool to do this is Whisken-Montanicity formula and blow-up technique, but I don't want to enter this kind of discussion today. So the only part that I will tell you is what is a singularity, basically. So we have our maximal evolution, with a maximal time. So there are 3 possibilities. Either the maximal time of evolution is plus infinity, and so in this case there is no singularity. Or if the evolution is only for finite times, then we have a description of what can go wrong at this singular time. And there are 2 possibilities. Either the inferior limit of the length of at least one curve is 0. So we have a topological change. So we have all my network that evolves at some point one curve disappears. Or virtue norm of a curvature blows down. These are not mutually exclusive. They can also happen together. What I do now for today, I give you example of this fact, and then I try to move on. Example of a...
Can I ask a question? I'm sorry.
Yes.
So can't it happen that it self-intersects? Say you have two components and one of them comes on top of the other. I imagine.
No, this cannot happen. So what is possible to prove is that you have so you don't have a maximum principle because you have a junction. However, you can prove that if you have some events like touching of two parts happen at the junction. So it's really one curve that disappear and two junction collision. You cannot have that two pieces that are far away, internal pieces of the curve that are far away at some point touches. This can be excluded.
Okay.
So
okay,
we have really a topological singularity.
Mm-hmm. Okay, thank you.
No problem. So case of a region that vanishes. So this is a computation that was already in the original paper by Mullins, but I think it's an extremely interesting paper because there are very nice examples. So what can you prove? You can prove that there is an evolution equation for the area and that the area evolves linearly. And what is this M? So this M is the number of curves that compose a loop. So if I have a loop, I can compute the evolution equation for the area inside of the loop. And I obtain that if M is equal to 6, so if I have 6 curves, the area remains the same during the evolution. If M is less than 6, I have that the area decreases linearly. And if M is bigger than 6, I have that the area increases. So if I have that M is less than 6, then at some point the area is going to 0. So when the area is going to 0, if I have certain symmetry, it's the easy case to prove it. You also have that all the length disappear. And when this length disappear, then the curvature is going to blow up. The normal curvature is going to blow up. And this is extremely easy computation. So this inequality here is a kind of Gauss-Bonnet argument. Again, I have minus M over 3 and not only 2 pi because I have the triple junction. And at the triple junction, I have internal angle of 120 degrees. So external angle, the jump of the tangent, external angle of 60 degrees is why I'm subtracting this M over 3. So this is basically Gauss-Bonnet. So let's recall the integral of kappa. And then here I use Holder inequality. And with Holder, I obtain kappa squared to the power 1/2 and length to the power 1/2. So since I consider M less than 6, so this is a positive quantity, I divide it by the length, when the length goes to 0, the curvature explodes. The of the curvature explodes. So this is the first example, the case in the L2 norm of curvature blows up. When I have the example in which two triple junctions coalesce, what is interesting in this case that if I have that one curve vanish, but it's not the boundary of a loop, it's not a loop. So there is no vanishing region, then the curvature remains bounded. So the idea of this proof is quite simple because really we are using as much as possible the fact that at the junction we have the sum of tangent vector that is 0, and we also have the sum of the curvature is 0. So with this information, one can develop extremely careful estimate that allows you to show that the curvature remains bounded. So there are examples in which this happens, that only one curve disappears. So first example, we consider a very symmetric situation. So we are symmetric with respect to this point. So we have a central symmetry. And we have that this two diagonal of this rectangle form angle that is like is bigger than 120 degrees, and it has to be strictly bigger. So if it is the case, then in finite time a singularity is going to happen, and this curve in between is going to disappear. And when this singularity happens, curvature remains bounded. Another example that is more tricky, for this case, we really need analysis of blow up. So here it's only analysis of Pdes. To do this, we really need all the power of Whisken monotracy formula. We need an analysis of blow up. So in the case we have this theta-shaped network that evolves, and the area are equal, then I know that if they are equal, they evolve with the same speed. So there are basically two possibilities. Or at some point the middle curve disappear, or the entire object disappear. But the entire object cannot disappear at once. And to do so, one has to prove that there is no shrinker that has the shape of a theta. So basically, you suppose that you have that everything disappears. Then you do a blow up to the point where everything disappears, and you try to classify what you see at the blow up. And since you cannot see a theta shape network because there are not shrinker of this shape, then this possibility is excluded. So this cannot happen. And so the only possibility that remains that the curve in between disappears. So these are two examples of this fact. So I think that these two examples are significant because in these two cases that we expect that are the type of singularity that happen more often, the curvature has not blown up, does not blow up. So this is very different from what we know from incurvature flow. In the case of incurvature flow, the singularity are cataloged with respect to how the curvature blows up. So there are different rates of blow up of curvature, but we and divide the singularity in type 1 and type 2. But in this case, we don't have a blow up. So this is a new kind of singularity. So we can think of this as a kind of type 0 singularity. So what is the moral of this story? The moral of this story is that even if we start from the very nice class of regular network, only triple junction and 120 degrees at the angle, this class is not preserved during the flow. And so at singular time, we can see what we can call irregular network. So either our network where at the triple junction, the unit tangent method does not sum up to 0, or there are network where we have more that free curves arriving at the junction. But also motivated by these cases in which the curvature does not blow up, it's very difficult to think about this as a real singularity because curvature doesn't blow up. So we are really tempted to try to evolve past this singularity. So there is a conjecture that, from what I know, is from Professor Ilmanen, that say that the flow can actually develop singularity. We have seen the example, but it is expected when only triple junction 4 points and 5 points appear during the evolution. So singularity where a lot of curves arrive at the junction are not expected during the evolution. In any case, even if we have a case with 3, 4, and 5 curves and nothing more, we have to find a way to pass the singularity. What I have not mentioned is the case in the fact when a region disappears, then the curvature blows up. But one can try to understand how the curvature of the remaining curves behaves. Because what we have seen in this integral is that we are integrating over the loop. So the curvature of these curves that disappears blows up. But one can try to see how the curvature of the remaining curve behaves. So maybe one can try to prove that there is some control of the curvature of the remaining curve. Because it's true that these things goes to infinity, and here you need that the sum of the curvature sum to 0, but maybe so you have some, I don't know, but okay, maybe this is something that one can try. So we know at least how the curvature of the curve, so we have some control, but we don't have really a theorem. Okay, after this, it's really the point to go through these singularities. And so this is the content of our theorem with George, Rafe, and Marielle. And this is a theorem that is somehow very related to the theorem by Ilman, Neves, and Schulze. So we have different techniques, and we work without monotonicity formula. So we don't try to reverse the monotonicity of formula. So we are not trying to using a monotonicity formula to go outside the singularity, but we use the micro-local analysis techniques. So what it is our theorem saying? So if we have an initial network that is of class 2, then there exists, and it is irregular, This means that we have junction with more than 3 curves that meet, or 3 curves that meet with the wrong angles. Then also in this case, there exists a positive time t and a Volpi family of network in this 0t, in this interval of time. And then we also have that in some sense, that I'm not specifying here, one can think Hausdorff, but it's more subtle, the NT, the evolution, converges to the initial data. And this I need because I need a relation with the initial data. One can think that you have some continuity. So the definition of how we converge is more precise, because we work in a blown up space and we have a smooth convergence in this blown up space. But to do this, I have to introduce what is the blown up space. So, but basically this is what I wanted to go through the singularity, because if I arrive at a singularity that I have curvature controlled, then I have a multiple junction, then I have this theorem here that tells you that I can go through the multiple junction. And also this theorem here tells you that before at the singular time you have a multiple junction, and for all time later you have again a flow with only triple junction. But it is my definition of a flow. So what I think is interesting about this theorem is that we have a classification of a possible flow out. And this is related to the number of possible expanding soliton that we have. So again, as to study the singularity, when you enter the singularity, you need some analysis of the soliton, the shrinking soliton. To go out the singularity, you need to study the expanding soliton. So to explain the theorem, before I explain a simple case, but it's the one in which one has an initial datum with only straight lines. So if I have an initial datum that is composed only by half lines, so we have a fan of half lines, then it's always possible to show that there exists at least one expanding soliton with this initial datum. So there is always at least a solution. So what is interesting is that this proof is not based on PDE argument, it's completely variational. So what is an expanding soliton? An expanding soliton is a solution that has always the same shape but magnifies during time. So we can write our curve gamma that depends on time and x, like lambda, that it is the parameter of expansion, times eta. And then if we do this ansatz, we suppose that we have the expanding soliton, and we put this in the evolution equation, we arrive to the soliton equation, to expanding soliton equation, but it is this one. So why this proof is completely variational? The proof is completely variational because expanding soliton are related to critical point of the length. So if I have my fan of half line, but I have some direction at infinity, I can think of this like, I can compactify, like to work on a ball, and I can think of this direction at infinity like points on the boundary. And then I can solve the Steiner problem, that is finding the minimal tree with these boundary points in this space, but it is not anymore R2, but it is a space with a different metric, but it is given by this one. So that it is a negatively curve. So one can think a little bit of the Poincare disk to have something in mind of what we are doing. So solving the Steiner problem is, so the Steiner problem is a very studied problem, very well studied problem, and also in metric spaces. And so there exists a solution. So there is always at least a minimizer. That is a network that has that boundary data given, but minimizing the length. And maybe a nice approach is done with currents with coefficient in a group, but maybe it's also a little bit overkill, so I don't know if it's the best approach. However, there is always a minimizer. So if there is a minimizer, we know that the minimizer is only composed by geodetic segment that meets a triple junction forming an angle of 120 degrees. And so since this is the situation, there is always a critical point and there is always a solution. So how can we put all together? So why these expanders are important? Okay, basically the point is as follows. Consider a situation in which you don't really have straight line, but you have curve. However, you have some thing that is related with a fun straight line, that is the direction of a unit tangent vector at the boundary, at the multiple junction. Suppose that there is a solution of a network flow, then think at each curve as a mapping space in time. So we are working in a RT plus, so we are positive time, and then in the plane for each curve. So we have, in this simple example, for curves, the number is not important, you can repeat the same argument, plus a new edge that we expect to see for all positive time. And this new edge will be defined on a P, that is defined for T positive and for X in this way. Instead, the edge that are already there are defined in 0, 1. So what I do a blow up both of the domain and also the range. It's needed to blow up both the domain and the range. The domain is kind of easy because the domain is 0, 1 times 0t, and in this case it's this P. So I have this corner here that represent exactly this point here in space and time. I blow up the corner. So what I do, what I mean with blow up, basically I do a change of coordinate. This is the change of coordinate. So when one realizes that in this blow up space, these coordinates are valid only here. There are extra new corners in which these coordinates are not anymore valid. But to fix the idea, I consider only this set of coordinates. When there are other coordinates to describe the other part of the blow up space. So this is the blow up of the domain. So basically it was 0, 0 that I didn't like. When I do the same also in the range, so this is my plane times the time, and I do a blow up of the origin 0, 0, 0. That is again the point in which I have a problem with, in which I have the multiple junction. Again, doing this blow up basically means changing the coordinates, and so I consider this set of coordinates. And again, this set of coordinates are not valid everywhere, but I focus on this. So basically, we always use free set of coordinates. Away from the origin, I will still use the old coordinates as x and t. On this part here, on this front face, I will use these 2 new coordinates. And then of the boundary of corner of the front face, I will use another set of coordinates because at some point this coordinate explodes, so they are not valid anymore. So what I have done like this, basically, I have enlarged my space in a way that now I can construct a solution in this blown up space. So I have enough space to put a approximate solution and to show that I have existence. So what does this mean with doing this blow up from the PD point of view? So I told you that it's basically changing the coordinates. And so this means that with this new coordinate, I can compute my parabolic equation with this new set of coordinates. So this was my old parabolic equation. Then I compute my equation with this new coordinate and arrive to something like this. And the equation is also, again, equipped with boundary condition. And also, we need an initial datum. And now we see which is our initial datum. So basically, I start from this equation here. And then I ask to myself what happens at tau equal to 0. And I realize that a part of the equation is 0. So this is the equation of initial time. But this equation is exactly the expanding Soliton equation is in a new set of coordinates. So my initial datum in the blown up space, so in my space that I have added, is an expanding Soliton. So here you can figure it out with a picture. So I have my problem, original problem. Then I do my change of coordinate. I blow up my problem. And now I see what it looked like my initial datum in this new problem. So here I have straight line because I've sent this part here to infinity. So this is infinity in my new picture. So I have only this reminder of how was the direction of the unit tangent vector. And then over here, I have my expanding Soliton. However, expanding soliton can be more than one. So if I have 3 curves that meet the junction, there exists only one expanding soliton, and this is the result by Schulz and Schnurrer. But in general, there can be much more than one, because the expanding soliton of the critical point of a Steiner problem. To be precise, I have a local minimizer of a Steiner problem, because I don't want expanding soliton with quadruple junction. So, okay, now this is the picture of my new initial datum, and then I have my evolution. So as I told you, the evolution is not unique, and I can give you one example in which we have more than one solution. So consider the case in we have a lot of symmetry, so this kind of cross. So I construct with arc of circle, but it's not important. So what I have in this initial datum, the important fact is that the unit tangent vector still sum up to 0, but form equal angle of 90 degrees. And then I want to triple junction, because I know that the evolution is going to have only triple junction, but I have a lot of symmetry. So the couple this junction into triple junction in this direction is exactly the same as doing the opposite. And indeed, if I look at the classification of expanding soliton in the case of this very symmetric situation, I realize that I have 2 possibilities. So these are 2 exactly the same valid solution. So I will have already 2 solutions. Moreover, so this is the case in which I focus on the network. But I told you that we had in mind the problem of grain boundary at the very beginning. So I can also focus on the case in which I consider the grains instead of the boundary. So the solution that I have described are surely valid if I consider that 4 different grains are meeting at the junction. So we have basically this. But from a physical point of view, I can also consider the fact that I have only, so that this space here is exactly the same as this here. So I have a set like this, so the red one is a set, or the gray one is a set. And in this case, what is expected is that the sets stick together during the evolution. And so it is reasonable also to consider a non-connected solution. And clearly with our theorem is also possible, because I can always find non-connecting expanding soliton. And so these are the 2 non-connected solutions. So in this case, if you are going to treat this like an evolution of the grain boundaries, you have also more solution. So to conclude, so here I give you only an idea of the proof through picture. So I have not given any detail what is the proper definition of my solution. So at this level, our result is very close to the result by Mann and Nevels and Schulze. However, if you look at the precise definition of our solution, we have a better understanding of how we restart the flow. And we have in the blow-up space more control on how we converge to the initial datum in the evolution. Clearly, when we blow down, we can expect too much, because if I start with the wrong angles, then I have a jump on the angle for positive time, so it cannot be C1. However, in this blown-up space, we have a smooth convergence. And okay, these are a lot of solutions. So clearly, more and more curves are meeting at the junction, more and more solution I will have, and the problem will become more and more complex. So for this reason, I think that the conjecture of Hillman is extremely interesting. So if one is able to prove that only 3, 4, and 5 curves meet at the junction at a singular time, this will make our life extremely easier, because in the case of only a triple junction, there exists only one expanding soliton. And in the case of 4 or 5 curves with the junction, the expanding soliton are not so many. So if one is able to do a partial proof or a proof something in the direction of a conjecture, then we will have a much better description of the flow. So I find that our short time existence theorem for irregular network is useful to restarting the flow. So now, at least combining several results that I mentioned today, at least in the case of a tree, if a network is a tree, then we know that we have a global solution, because when I arrive, say if I have a tree, So under a strong hypothesis on the blow up, but I have not mentioned really what is blow up in this talk, so I cannot also describe exactly what is the hypothesis. So if I have this, the multiplicity 1 of the blow up, then in the case of 3, I will have only this kind here of singularity in which the curvature remains bounded. So in this case, with the theorem, we can start. And so one can have a solution for all time. And so for this point of view, it becomes also more important to describe what happens when t goes to infinity. For the moment, we are able to show up to such sequences that one converge to a critical point of the length. And we hope to have an improvement of this with a paper with Pozzetta, and we really be able to prove that there is a full convergence. And for this, we hope we are able to use Lojevic-Simon inequality, but this is still work in progress. Thank you very much for your attention. I can stop here.
Sorry, took some time. Thank you very much. I'm trying to get the soundbox to run. If not, I clap myself. So I stopped the recording.